This is on mathematical proofs using the procedure of math induction. The idea of math induction is this sort of domino effect that you show something is true initially, you show it's true for each sequential one after, and therefore it's true for everything after. So the steps, or the theory, show the statement is true for n equals 1, assume the statement is true for n equals k, and then show that the statement will be true for n equals k plus 1, given your assumption from step 2. So you show it's true initially, and then you show it's true basically everywhere thereafter. So here are a few examples. Alright, we have this statement which we're trying to prove. So we're not trying to come up with a statement, we're just given a statement trying to prove it. And so the first thing is to show it's true for n equals 1. So that means the first term of all these. So just the first term is 2. You plug in 1 for here, you get 2 equals 1 times 1 plus 1, which is true. Then you assume it's true for n equals k. So assume it's true that this is true, 2 plus 4 plus 6 and so on, plus 2k is equal to k times k plus 1. Now given that, we want to then show that it's true for the k plus first term. So after 2k, the next one is 2 times k plus 1. This k becomes a k plus 1. This k becomes a k plus 1. So we want to show this is true. The way to do this, after I simplify this a little bit, by just distributing the 2 and fixing up this, is to subtract step 2 from step 3. If you take this whole thing and you subtract this whole thing, then on the left side, all you have left is 2k plus 2, because all of these terms cancel out. And on the right, you have k plus 1 times k plus 2 minus k times k plus 1. And so we do a little algebra, 2k plus 2, and we distribute all this and see if it's correct. And it is. 2k plus 2 is equal to all this, 2k plus 2. So that's true. So this is true by mathematical induction. Here's another example. We want to show that this statement is true. The sum of n cubes is equal to this formula. So first of all, show it's true for n equals 1. So that's 1 cubed. The very first term is equal to 1 squared. There's 1 plus 1 squared over 4. Well, that is correct. 1 is equal to 1 times 4 over 4. So that's true. Assume it's true for n is equal to k. So same thing, but with k's instead. And now given that, we want to prove that it's true for n equals k plus 1. So the term after k cubed is the k plus first term, so k plus 1 cubed. This k becomes a k plus 1. This k becomes a k plus 1, so k plus 1 plus 1 is k plus 2. So then, we algebraically will do it in a similar way as the last one. We will subtract the second one from the third one. So all the terms on the left cancel out except for k plus 1 cubed. And on the right, we have all of this stuff. I factored out a k plus 1 squared over 4 to make it a little bit easier to do the algebra. That's how I got to this step when I did this part minus this part. So I factored out k plus 1 squared over 4. And then what you can do is divide off a k plus 1 squared from both sides. So the left is just k plus 1. And the right then is going to be a 1/4, because you left the 1 up here. And I distributed all this stuff. And it turns out these all cancel out, and you get k plus 1 is 4k plus 4 over 4, which of course is true. Another example. Same steps. So apparently this is true. Let's try to prove it using mathematical induction. So first, show it's true for n equals 1. So this is the first term, 1 plus 1 over 1 is equal to 1 plus 1, that's true. 2 is equal to 2. Assume it's true for n equals k. So here, all multiplied together, k, and this is k plus 1. Now we want to try to show, given that it's true for the k plus first term. So we need these terms times 1 more is equal to k plus 1 plus 1, which is k plus 2. Now notice we're not adding terms on, we're multiplying them. So to simplify this, rather than subtracting as we did in the last two examples, we're going to be dividing. We divide this expression, this whole equation I should say, by this whole equation. So everything divides off except for 1 plus 1 over k plus 1 here, and over here k plus 2 over k plus 1 gets us there. And we want to show these are the same. So I took the left side and I got a common denominator, k plus 1 over k plus 1. I put it into a single fraction, and then this of course is just k plus 2 over k plus 1. So it does work. This is another type using inequality. So here we try to prove an inequality using math induction. So first show it's true for n equals 4. You don't start at 1 because we're going to be greater than or equal to 4. 4 factorial is greater than 2 to the 4th, which is true. Assume it's true for k n equals k, so k factorial greater than 2 to the k. Show this is true. K plus first term, we divide first. And so we get k plus 1 factorial over k factorial. That simplifies to k plus 1 greater than 2, so k is greater than 1, and then it's greater than or equal to 4.